actually here to talk to you about is near-infrared polarimetry on NIRC2. So my name is Briley. I'm a postdoc at UCSB, actually recently former grad here at UCLA. And what I'm talking about today is actually a huge team effort over a time that actually goes back to before I started grad school. So there are a lot of people that were involved in making this possible. But I get to be the one to come here today and tell you that this mode is actually almost ready finally. So we are bringing an AO-fed infrared polarimetry mode to Keck. So you'll actually be able to do imaging polarimetry with NIRC2. The PI of this mode is my advisor at UCSB, Max Miller-Blanchard, and I'll highlight some other UCSB folks that have contributed a lot to this throughout the talk. So why do we care about polarimetry? So often in astronomy, we are measuring, the amount of light or the wavelength of light, but we can actually also look at the orientation of light and get extra information that way. Light can be linear, circular, or elliptical polarized, and we often measure it with the Stokes vector. So this is IQUV, where I is the total intensity, Q is two orthogonal polarizations, U is 45 degrees from that. And the things aren't rotated on the slides. Those should be at a 45-degree angle. And V is circular polarization. For astronomy purposes, we basically only deal with linear polarization. So this polarimeter, like many other astronomical polarimeters, can only measure linear polarization, but that gets you a lot of interesting science cases. The basic design of a polarimeter like this, we call it dual channel polarimeter, is that you have your regular telescope optics, but in addition to that, you have a half wave plate that is able to modulate the polarization state. This is useful for calibration and for getting those Stokes vectors out from your measurements. And you have a Wollaston prism, which is a polarizing beam splitter. So this is going to split your light into two orthogonal polarization states to be recorded at the detector. The Wollaston was actually installed in NIRC2 quite a while ago in February 2019. This was before Max gave the last talk at Keck Science meeting about NIRC2 polarimetry. But now we can say that both components are in. We just installed the half wave plates in NIRC2 last month. So those are up there. Thanks to the Keck team for making that possible. And so we have two rotatable half wave plates in there. We have one for JH and K bands and one for L band. There are a lot of different science cases that you can use this polarimeter for. So the one that I'm personally most interested in is circumstellar disks. So often when we image disks, we have to deal with getting rid of the bright light of the host star. These faint disks are around, and polarimetry provides a very clean way to do that. So the light from the host star is unpolarized. The light that is scattered off the small dust grains in the disk is polarized. So you have this natural separation you can take advantage of if you can record in polarized light. But there are so many other science cases too. You can look at clouds in brown dwarf atmospheres. There are cases at the Galactic Center for AGN, for the solar system, for supernovae, and more. And we've already heard a lot of great science cases from the community. So since this is something that you might be able to use soon, figured I'd tell you about the capabilities of it a little bit. So like I said, we can do JHK or L-band polarimetry. Instead of the regular 10 by 10 field of view, the field is split in half, so it's 5 by 10. You can use natural guide star or laser guide star AO, and can combine polarimetry with a lot of existing NIRC2 modes. So we can do GRISM spectropolarimetry, imaging polarimetry, and high contrast coronagraphic polarimetry. So there are a lot of possibilities with this new mode. To give you an idea of what I mean when I say that the field of view is split, so if you have your full field of view, we put this rectangular mask on to basically cut the field in half so that we can fit two images on the detector for each orthogonal polarization state without them overlapping. So on the right is what you'll see after the mask on the detector. This is a kind of old design concept, but we'll hopefully get the idea across that we have this insertable rotation stage that can be put in and out of the beam. And this is shared with the pinhole calibration unit, which is led by Jessica Liu and Charles-Antoine Claveau at Berkeley. So there's essentially this one mechanism that you can switch out the pinhole calibration unit for precise astrometry with the two half-wave plates. And the fact that the wave plates have to be switched out is actually an important constraint for observing. Since there's one for JH and K and one for L, and they have to be manually switched, you can't do both JHK and L in the same night. So that is one important constraint. I have a bunch of fun installation pictures to show you. So this is the Wollaston Prism. It's made of yttrium orthovanadate, which we chose because it actually splits at a similar angle across all of the bands we care about, so it just makes things more consistent. And I always think pictures of optics are very fun. That's part of why I do instrumentation. This is initial on-sky data with the Wollaston from back in 2019, showing that we are, in fact, splitting the beam in two, so that is working. But why I'm here today is to share all of the new status updates that have happened since. So we got the two half-wave plates delivered to UCSB a few years back, and they've been really rigorously characterized in Max's lab at UCSB. So both half-wave plates are within 10% of their target retardants, and we've characterized all sorts of other properties about them, like the throughput, beam walk, all sorts of things. And this work was done by two really great students at UCSB for the most part. Rebecca Zhang, who's a current grad student and is leading commissioning for this instrument. That's her thesis. And now U of A grad student, former UCSB undergrad, Will Melby, did a lot of great characterization of these as well. So we very confidently know a lot of the properties of these half-wave plates because we are aiming for a very precisely calibrated instrument that we can use for quantitative polarimetry in addition to qualitative polarimetry. These are the half-wave plates in the lab in their custom designed mounts. So like I said, they're installed with the pinhole calibration unit. That's part of the mechanism for it on the right. But that's both of the half-wave plates in their mounts in the lab. And in June of this year, we finally shipped the half-wave plates to Keck. So Rebecca and I got to, put on the clean room stuff and get them all packaged up and sent off. I think it's really interesting how they are so clear that you actually can't really tell they're in the mounts at times. And we sent them to Keck in these cool custom designed 3D printed cases that were made by an undergrad in our lab, Thomas McIntosh. And yeah, that's again Rebecca. She shows up a lot in this. She has done a lot of work for this mode. So in August, about a month ago now, the half-wave plates were installed at Keck along with the PCU. That's Rebecca on top of the AO bench. And now she's been there as a Keck visiting scholar for a bit. And we have proof of life that, it's there and it's modulating. So you can see in this GIF, as we rotate the half-wave plate, we are seeing modulation like we expect. And the plot shows the same thing. That's Rebecca and Max at Keck for the installation. So what are the next steps here? Like I mentioned a lot, Rebecca is doing a lot of this. She is currently there working on software and daytime testing for pole mode. I'm going to join her in a few weeks to hopefully help get through commissioning. And we have on-sky engineering and commissioning time in 25B to make sure that this mode is operational. Part of that came from the UC TAC, which has been really helpful for making this all happen. We have plans to create an open source data processing pipeline for NERC2 pole so that it is easy to, process your polarimetry data. And to make a Mueller matrix model for calibration, like I said, to make this as precisely calibrated as we can, kind of like Subaru, Skexiocaris, and vampires. We're hoping to do science verification in 26A. We got a lot of great science cases from the community, including many people who are in this room, and we're really excited about that. And the goal is to be ready for open use for 26B. NERC2 has, a limited lifetime as scales comes online and NERC2 is decommissioned in the coming years, but there is so much that we can do with this mode before that. So propose for it when it's open. I also wanted to thank the support astronomers for making all of the commissioning we've been doing so far possible and all the daytime testing. It really has been a team effort to make this mode possible. So long story short, get excited for the new NERC2 pole mode. It is really almost here and ready for you to use. So AO-fed IR polarimetry is going to be on NERC2 and available for open use as soon as 25B. You can use a bunch of the existing NERC2 features that you know and love now with polarimetry. Parts are installed, commissioning is happening, and there will be a data processing pipeline, hopefully before 25B, for you to use. We're trying to make it as easy as we can for you to do really cool science with NEARC2 Pol. This is going to be a really, really unique instrument. There are not many 8 to 10 meter class telescopes with infrared polarimetry, especially in L-band. So this is a really, really unique opportunity that we are excited to bring to Keck. And I'm happy to take any questions.